In this video, we're going to be talking about comparing two populations or treatments. Specifically, inferences concerning the difference between two population or treatment means using paired samples. So suppose that an investor wants to determine if regular aerobic exercise improves blood pressure. A random sample of people who jog regularly and a second random sample of people who do not exercise regularly are selected independently of one another. Can we conclude that the difference in mean blood pressure is attributed to jogging? Well, what about other factors like weight? One way to avoid these difficulties would be to pair subjects by weight, then assign one of the pair to jogging and the other to no exercise. So a summary of the paired t-test from comparing two populations or treatment means we have our null hypothesis. So we have our mu sub d, which is the mean of the differences in the paired observations, and that's going to equal our hypothesized value. Our hypothesized value is usually 0, meaning that there is no difference. Our test statistic is t equals x bar sub d minus our hypothesized value divided by the standard deviation of our sample sub d divided by the square root of n. So again, n is the number of sample differences, and x bar sub d and s sub d are the mean and standard deviations of the sample differences. So this test is based on degrees of freedom of n minus 1. So what about our alternative hypothesis? So if we have that our mu sub d is greater than our hypothesized value, then we're going to take for our p-value the area to the right of our calculated t. If for our alternative hypothesis we have mu sub d is less than the hypothesized value, then for our p-value we'll be taking the area to the left of the calculated t. And if our alternative hypothesis is that mu sub d does not equal the hypothesized value, then we're going to take 2 times the area to the right of t if we have a positive t, or we're going to take 2 times the area to the left of t if t is a negative t. We have our assumptions that we have to go through. So first, the samples are paired. Second, that the sample size differences can be viewed as a random sample from a population of differences. And third, that the number of sample differences is large, so generally at least 30, or the population distribution of differences is at least approximately normal. So is this an example of paired samples? An engineering association wants to see if there is a difference in the mean annual salary for electrical engineers and chemical engineers. A random sample of electrical engineers is surveyed about their annual income. Another random sample of chemical engineers is surveyed about their annual income. No, there's no pairing of individuals here. So you have 2 independent samples. Let's look at another one. Is this an example of paired samples? A pharmaceutical company wants to test its new weight loss drug. So before giving the drug to volunteers, company researchers weigh each person. And after a month of using the drug, each person's weight is measured again. What do you think? Yes or no? Yes. You have 2 observations on each individual, resulting in a paired data. Let's look at another example. Can playing chess improve your memory? In a study, students who had not previously played chess participated in a program in which they took chess lessons and played chess daily for 9 months. Each student took a memory test before starting the chess program, and again at the end of the 9-month period. Here we see our data. For the 12 students, we have our pre-test, our post-test, and the differences. So first, we find the differences between our pre-test minus the post-test, which we see here in red. Now we want to state our hypotheses. So here, our null hypothesis is that there is no difference. An alternative hypothesis is that it's less than 0. So here our mu sub d is the mean memory score difference between students with no chess training and students who have completed chess training. Something that's important to note here is that if we had subtracted the post-test minus the pre-test, Then the alternative hypothesis would be the mean difference is greater than 0. Let's continue on. Now we need to verify our assumptions. So although the sample of students is not a random sample, the investigator believed that it was reasonable to view the 12 sample differences as representative of all such differences. Second, a box plot of the differences is approximately symmetrical with no outliers, so the assumption of normality is plausible. Now we're going to compute the test statistic and our p-value. So we'll go ahead and we'll plug in our values, giving us a negative 4.56 for our t-value. Looking that up in the table, or using our calculator, gives us a p-value that's approximately 0. And we have a degrees of freedom of 11, and we'll use an alpha of 0.05. So now we're going to state our conclusion in context. So since the p-value is less than alpha, we're rejecting the null hypothesis. There is convincing evidence to suggest that the mean memory score after chest training is higher than the mean memory score before training. So when do we use a paired t-confidence interval for our mu sub d? Well, first, when the samples are paired. Second, the n sample differences can be viewed as a random sample from a population of differences. And third, the number of sample differences is large, so generally at least 30, or the population distribution of differences is at least approximately normal. So when we have that, we're able to have a paired t-confidence interval. So the paired t-interval for mu sub d is x bar sub d plus or minus our t critical value times our s sub d divided by the square root of n. Again, where our degrees of freedom is n minus 1. Let's go back to our test problem. We're going to compute a 90% confidence interval for the mean difference in memory scores before chest training and the memory scores after chest training. So we'll go ahead and we'll plug our values into our formula, giving us an interval from negative 201.5 to negative 87.69. So now, how would we put this into context for our, with our interval? So we're able to say that we are 90% confident that the true mean difference in memory scores before chest training and the memory scores after chest training is between negative 201.5 and negative 87.69.